Okay, so we've looked at two of the rules that we use, so the product rule and the quotient rule. We're going to look now at one last rule that we're using with general derivatives, and it's called the chain rule. And kind of you can tell a little bit, I suppose, from the name. The idea of the chain rule is maybe we're chaining functions. So where we have what we'd call a composite function, so a function of another function. And when we have that, what we do is we can label our two functions like u and v as we've kind of done before, or maybe what we'll do more often is maybe just label one of them, and we'll use a substitution for that one. And we can find the derivative then of my overall function with respect to that substitution, and then the derivative of my substitute function with respect to the variable in question. What we're always aiming for is what I've highlighted here in yellow. So this idea that dy dx is the same as getting dy du, where u would be my substitution. So where u would be my substitution, and then getting du dx. And if we look at that idea there, we have a du and a du, and they will essentially kind of cancel each other out to give me that dy dx part. And where the chain rule comes up a lot is with powers. So like the example here where we maybe have an expression in a bracket. So x plus 2, we know how to do the derivative of that, but then it's all to the power of 3. And that's considered a composite function because it's an expression that is then all cubed. So it's a function within a function. So in that sort of case, we might say that my substitution would be x plus 2, and then the original function y could be rewritten as u cubed. And we can do the derivatives for each of those. We don't know how to do a derivative of x plus 2 all cubed in any other way. So using the chain rule, we kind of think about working from the outside, working our way inside, and if we have additional derivatives, we're going to multiply by those as we go. So we can use our substitution, or we can use this general way of thinking about the chain rule to tell us what to do. And we're going to see how it applies to the different examples that we're looking at. But as I've said already, the main telltale sign of the chain rule is really expressions with powers then, where you have an expression and it's all to the power of something, where we have a bracket that's all raised to a power. So here for this example, we could rewrite this as y is equal to 4x squared plus 1 all to the power of a half. So this here tells me it's going to be a chain rule because I have an expression that is all raised to a power. So if we were to follow it kind of explicitly, we might say that u is going to be the inside expression here, the 4x squared plus 1, which then of course means that y could be rewritten as u to the power of a half. I can get my derivative of u with respect to x. It's going to be with respect to x because x is the variable in this u expression, and that's going to give me 8x. And I can get the derivative of y with respect to u. This time I'm using u on the bottom because my expression, my function in y here, is in terms of u as a variable. And that would give me a half u to the power of minus a half. To get the overall derivative dy dx, I will take dy du multiplied by du dx, just taking these from above. So dy du dx here, and dy du here. So dy du, we know already, is a half u to the power of minus a half, multiplied by du dx, which is 8x. And the last thing I need to do is kind of simplify and sub back in for u. So I end up with a half 4x squared plus 1 times 8x, which is going to give me 4x times 4x squared plus 1, so it's to the power of minus a half, to the power of minus a half. And I could rewrite that if I wanted then, using my indice rules, as square root on the bottom. And that's my value for my derivative. Okay, so that is us taking our explicit substitution there and working that out in full. The other way we could take it is kind of that idea of working from the outside in. So I can see there immediately that I have two different parts to worry about. The first part is that I have a derivative of using this power. So I have an expression to a power, so I need to differentiate that. The other part I need to do then is I need to do the derivative of what's inside the bracket as well. So if I do my dy dx, then first of all, we're going to have the derivative of the power part. So we know that generally our rule is multiply by the power and reduce the power by 1. But in this case, I need to multiply by another part as well, which is the derivative of what's inside the brackets there, the derivative of what's inside the brackets. Okay, and let me just see, actually I've swapped the colors there, so let's just make them the same as we had on the left hand side here. So we'll make this purple color, and we'll make the other one the orange. Okay. So same idea applies. So I'm just trying to keep it as related as we can so that we're not confusing them more. So the middle part there giving me the 8x, and the outside part, the power part, giving me that a half, 4x squared plus 1 to the power of minus a half, and we end up just with the same result, 4x over the square root of 4x squared plus 1. So the same result either way, we're doing the same steps either way. We've two derivatives as we had in the first stage. The only difference we're doing on the right hand side is we're not labeling that u part. And some people might like that and some people might dislike that. So it really depends on what you're feeling. It is never going to be detrimental to use that labeling, and sometimes we might want to call it u, we might use maybe z or something different, and it doesn't really matter. It's not going to throw off the question all that much for you either way, but it's just important to remember what you need to be, or kind of the general steps you're following here. So looking at this question, f of x, let's rewrite the function first of all. Okay, so I'm going to rewrite this function as 5x squared plus 7 to the power of minus 1. Now we might look at this question and say I could use a quotient rule, and absolutely you can use a quotient rule. I'm just going to show how we would do it using the chain rule. So working from the outside in, I have two derivatives here. I have the fact that it's an expression to the power of minus 1, and I also have the derivative of what's inside the brackets there to deal with as well. So if I was just to take this in this kind of quick fashion, first of all, to find my derivative, I would do multiply by the power and reduce the power by 1, so minus 2, and I need to also multiply by the derivative of what's in the middle, which is 10x. Okay, simplifying all this down, I get minus 10x over 5x squared plus 7 squared. Taking on the left hand side here, let's just do it more explicitly. So let's say that u is what I have inside the brackets, 5x squared plus 7. I can then rewrite my original function as u to the power of minus 1. du dx is going to be 10x, and dy du is going to be minus u to the power of minus 2. Okay, taking my parts as before, let's do our two derivatives here. So dy dx is dy du times du dx, making sure we're lining up those du parts. So dy du is minus, let's fill in what u is, so 5x squared plus 7 to the power minus 2 times my 10x, and I end up with the same result as I had on the right hand side there. So either way works, and we should be able to see how I would maybe move from one to the other. Okay, so all we're doing is on the left hand side we're being more explicit about that substitution. On the right hand side we're just we are doing it, but we're just doing it a bit more kind of fluently without having to really explicitly label that substitution there. So let's just keep going then and have a look at an exam question or two here. So the first exam question from 2012, again, differentiate with respect to x. So we've the same idea going here. We have a power part and we have what's inside the brackets. So to find my overall derivative, my dy dx, first of all, I'm going to multiply by the power, the 3, and I'm going to reduce the power by 1. But we have to remember that in this case as well, because we have an expression within those brackets, we have to multiply by its derivative as well, which is 8x. So overall, I get 24x times 4x squared minus 1 squared. Okay, just bringing everything together there. Looking then at this last example, this is from the 1974 paper, and this is using chain rule with the quotient rule. Okay, so we have kind of a few different parts going on here, and this is maybe where understanding what's happening is more important than those substitutions to some extent, because these can just end up confusing things all the more for us here. But let's just do it out maybe explicitly so that we can have a look at how it all relates here. So I can rewrite this as x over x plus 1 all to the power of a half. All to the power of a half. So let's make a substitution. Let's call this z. So I'm going to rewrite it as z to the power of a half. Okay, let's take z over here. So z is equal to x over x plus 1. So I have u and I have v for my quotient rule. So u is going to be x, v is going to be x plus 1. Okay, that means du dx is just 1, dv dx is also just 1. So finally my quotient rule, which is going to be dz dx, because remember I've rewritten this function now as z, dz dx is going to be x plus 1 times 1 minus x times 1 all over x plus 1 squared. And reducing all this down, I get x plus 1 minus x all over x plus 1 squared, which is of course just 1 over x plus 1 squared. So that is dz dx, and that's going to be important. Let's just label that and highlight it for ourselves there. So now that I've rewritten that, I can rewrite my original function as we've done up here and rewrite it as z to the power of a half, which means that dy dz is a half z to the power of minus a half. If I want to find dy dx, I need to use dy dz times dz dx. Okay, the only reason here that I've used z for that substitution is just because I knew I was using the quotient rule, and in our quotient rule we use those letters of u and v. So I thought it would be more confusing to use u, so we just called it z instead for our chain rule there. So dy dz was a half z to the power of minus a half times dz dx, which is 1 over x plus 1 squared. Let's just fill in for z here in those places. So z is, again, is x over x plus 1 to the power of minus a half times 1 over x plus 1 squared. 1 over x plus 1 squared. Okay, now if we want to reduce this down a little bit further, it's just a matter of, I suppose, using our algebra. This maybe is where things get more confusing. We could split this part out here and write it as x to the power of minus a half over x plus 1 to the power of minus a half, and we're multiplying by 1 over x plus 1 squared. Okay, if we're multiplying those bottom parts, so these two parts here, we're going to be adding the powers. So 2 plus minus half is going to be 3 over 2. So I'll have a half times x to the power of minus a half over x to the power of 3 over 2. X to the power of x, sorry, not x, x plus 1. X plus 1 to the power of 3 over 2, and we can probably just bring this all together as 1 over 2 root x, x plus 1 to the power of 3 over 2. Okay, so complicated enough ending to our question there, but the actual basis for it remains the same. So following through with chain rule and quotient rule in one, if we were to take that simpler and kind of without those kind of few substitutions, all that it really saves us is that kind of initial z part really. So multiplying by a half, reduce the power by 1, and we would end up with kind of our same result as we had in the middle part there, and multiply by the derivative of the middle. It's finding the derivative of the middle that could cause some issues there. But the main idea with the chain rule is just to kind of pick whichever way works for you. If you want to do the substitutions out fully each time, absolutely. If you're kind of okay with taking that idea of working from the outside in, doing each of those derivatives as we encounter them. That's going to be the idea that we're kind of running with for some of the other derivatives, the trig derivatives, the exponentials, and so on. So it's a good one to get into a habit of, and it will save you a little bit of trouble when we get to those, say for the trig ones, for example, where we maybe have three additional parts to consider.